I'd like to introduce to you PC-Train Smart. PC-Train is a nuclear power plant simulator, and SMART is a Korea Atomic Energy Research Institute (KARI) design small modular reactor. It is about the size of one-tenth of a large typical power plant. The thermal power is about 330 megawatt, and the electric power is about 110 megawatt electric without heat uh, application to desalination or district heating. It does have the capability to produce uh, desalination water using a fraction of the low pressure turbine steam, and up to 40,000 tons a day can be produced if the electricity is reduced to about 90 megawatt electric. Uh, Here is the core and the control rods on top is mostly withdrawn during full power operation. And right now the reactor is operating at about 15 megapascal. That's about the same as other larger PWR. The steam generator pressure is about 5.5 megapascal. It's different from the typical PWRs. The reactor pressurizer is inside the vessel on top of the core. And also the steam generators, one through helical coil steam generator, there are 8 of them. We modeled them into 2. The feed water going from the bottom is spiral core and heated by the react cooling hot water becomes steam, and the steam is superheated because of one through steam generator, and the steam going to the turbine and the generator, and they're condensed in the condenser and a number of heaters and pumped back into the reactor. During normal operation, the power control, if we desire to have a slight reduction to 80%, you can either manually operate it by inserting the rods and adjust all the other pressurizer, feed water control manually. But we do it integrated way. So we reduce the power of the turbine, and right now the simulation is 1-to-1. The atom sign with electrons spinning around the nucleus symbolize it's in operation, and 1 means real time. We can speed it up to 2 or 4 times, up to 16 times faster. That's simply for education classroom convenience. So the variables will look at the power of the core thermal power, the neutron flux, and the turbine load. Click OK, and the time span in seconds. You see the power drop to 80% in 2 minutes. That's the turbine, the blue, color coordinated. The green is the neutron flux, and the red is thermal power. They follow each other very closely because the control system in place. And the pressurizer is controlled by the heater and the spray. So you see the pressure of the steam, the primary side and secondary side. since the original pressure is about 15.5, so I put the range at 20. You see the primary pressure almost constant, and secondary pressure slightly go up because of the reduction of power and designed that way. And you can also see other variables such as the temperature of the primary hot leg and cold leg. And let's make the range 200 to 400. That's in Celsius. See, that's a hot leg temperature, cold leg temperature. The delta T reduced because of power reduction. In case we shut down the plant, we can simply click here that all the control rod go in, and the system will be stabilized in a post-trip condition. And the heat removal after reactor shutdown is by the condenser. You see the turbine stop valve is closed. Turbine was pink, symbolizes of rotating, and now it's blue, symbolizes no longer generate electricity. Most of the steam will go to the condenser. Suppose we lose, and the reactor will cool by the steam generator and a normal shutdown system. Suppose we lose the offside heat, offside AC power, then the SMART has a passive way to remove heat by opening the valves of the from the steam generator's side and condensed in the passive heat removal system. It's a very large pool with 200,000 kilograms of water physically above the reactor vessel. In outside containment, that's an atmospheric pressure. So the steam will be condensed in the heat exchangers in the pool and return to the steam generator feed water side. So our decay heat now is 8 megawatt. And the passive heat exchanger also removed the same amount of heat. So this pool will keep the reactor decay heat removed and the core submerged underwater for up to 3 days. All right. In case we have a loss of coolant accident, well, there are all kinds of accidents, anything possible or foreseeable. We'll have a cold leg, because the primary coolants are inside the reactor vessel. There's no possibility to leak outside other than the piping connection. So the feed water line break, a loss of outside power, or turbine trip, tube rupture of the steam generator, anything could happen, right? So we can simulate that by assuming we have a feed water line break, and the size, let's just put 100 centimeters square, and the run, you see there's a break here. So as a result, the primary pressure will be falling down rapidly. As a result, the safety injection pump will start automatically. It's a diesel generator powered, put water back into the core. if the pressure continue to go down, and containment pressure will go up because of the loss of coolant through the feed water line. See, now the pressure inside the containment is 0.28. That's about 2 times 8 of atmospheric pressure. Soon the containment spray will also turn on. And that will spray into the containment to reduce the pressure. You see the pressure is going down now. And we can also look the transient plots. See, this is the temperature. And we can see the primary reactor pressure of the reactor coolant and the reactor building or the containment. Minimum is 0 and maximum is 20. See, this is our reactor pressure, originally 15, and because of steam loss, it go down, and after reactor shutdown, it go down considerably to almost the same as the and containment pressure originally is atmospheric pressure, and now it's about the maximum was 3 times, but now it's cooled down to 2 atmosphere. Actually, less than 2. Okay, so this is a small modular reactor. The advantage is it's extremely safe. It is compact in size, and one side typically holds 2 units. So combined, it would generate 200 megawatt electric and provide desalinated water and process heat for a small city about a couple 100,000 population. This could be used at either remote place short of water supply, or community close, heavily populated, because it's very safe. That you have lesser licensing requirement. So this is a brief introduction. Hope you get an idea of the smart reactor. Thank you.